This is Dr. S.P. Arsa from Mechanical and Industrial Department, IT Roorkee. I'm going to deliver my lecture 36 of the course of the strength of materials, and this course is developed under the National Programs on Technological Enhanced Learning. Now you see here, prior to start this lecture, we have almost done about the beams, beam theory. You see what the bending stresses are there, what the torsional stresses are there in the beams, and then you see there are lots of theories are there through which we can calculate not only the deformation but also the deflection part, and then you see in the last part we have we discussed about the theories of failures, and we found that when a beam is subjected by both of them, that means you see when the combined loading is there, then there are a lot many ways are there to describe those stresses, and that's why you see there are various theories of failures are there. As we have seen the lecture 34, that when the combined loads are there, that means you see when a beam is subjected by a bending stresses as well as the tensile stresses, then how we could figure out the equivalent stresses, like in terms of the bending or in terms of these shear, or rather we can say in terms of the torsional part. And then in the previous lecture, you see we discussed about when there are 5 different ways to describe the failures of theories, and you see all those theories they're invented by some of the mathematician or the physician. So that's what you see we known these theory by their own name, like you see the Rankine or Haig, or there are the Tresca's theory. So there are a lot many things are there in that. So we started from the maximum principal stresses, that you see when we equate that part which is equivalent to the maximum principal stresses in a particular plane under the variety of the load conditions, then where you see it is going to be fail. And then with that you see we ended with the total strain, the maximum shear strain energy per unit volume, in which also we found that you see how the relative terms are there of this normal stress component with the because it is absolutely based on the maximum shear stress part, maximum shear strain energy. So how much energy is being gained under the load different load conditions. So that part we discuss, and you see along with that we discussed about the maximum principal strain part, the maximum shear stress part, and then you see the maximum strain energy per unit volume, and then last one was there the maximum shear strain energy per unit volume, in which you see when the shearing is there, due to the shear action we have the strain energy, and you see under the action you see what the relative reference frame is moving with respect to the sigma 1 minus sigma 2 or sigma 2 minus sigma 3 or sigma 3 minus sigma 1, and how we can compute and to equate with the sigma yp, that means the yield point in that. So these were few of the 5 theories of failures were there, which we discussed briefly about to calculate about the ductile material, because this is very important to rectify because all these theories were there under the elastic failure. So we need to clearly define the reasons of elastic as well as plastic, so that we could easily figure out that okay, now within this elastic failure, this could be happen if it is reaches up to sigma yp, due to maybe the principal shear stress, due to principal stress, principal strain, maximum shear stress, strain energy, maximum shear strain energy per unit volume. So all these things these 5 theories are always just try to approach up to sigma yp, and then we are equating to get the real feeling about the failure theory under those prominent parameters. So this we discussed in the previous lecture. So now this is almost done. We are done with the kind of beam part. So now we are going to focus on the column. So instead of beam, now if we have a column, then what will happen? So you see here, this lecture is mainly focused on, as I told you, the elastic stability of a column. But again we need to define the boundaries which can clearly identify that what will be the column or the strut is. So in in this particular, we have the structural members which carry compressive loads may be divided into 2 broad categories depending on their relative lengths and the cross-sectional dimension. So that's what you see here. These are the 2 influencing parameters through which we can simply bifurcate that which one is the column and which one is the strut. And these 2 important parameters are what is the relative lengths are there and what is the cross-sectional dimensions. That means what the dimensional parameters are there through which we can say that we can keep this thing in a column, we can keep this thing in a strut part. So the first thing is the column, the short thick members. So if we have a short member, again it's a very relative term. Sometimes you can say this short is a long, but because nowadays we are always talking about the nano or micro level, so obviously this somewhat the millimeter or the centimeter is the tall or long terms. But in relative frame, you see, we can say the short and the thick members wherever the applications are there are generally termed as the column. And these, like usually fail by crushing when, like the yield stress of material in compression is exceeded. So you see here, when you are simply compressing and you see due to that compressive part, if there is a crushing is there, means the layers are, like exactly crushing to each other, they are simply overlapping to each other. And if the yield stress is approaching up to that point, we have a failure part in these columns. So you see here, we are defining in terms of their dimensional part. And the second part is the strut. Struts are nothing but, you see, like the longer, the slender columns, we can say, are generally termed as the strut. Means, you see, they have the long, not thick, they are the thin part, you see, and we can say that whatever the these theories are coming, they have to be spread it out in along the transitional way. So they fail by buckling, because you see they have the longer part, so obviously the buckling is an important parameter to check it out the failure. So they fail by buckling sometime before yield stress in compression is reached. So this is pretty sensitive part that you see when we are defining, when we are keeping a thin line in between the column and the strut, then we have to be very, very careful that if you are taking in a length and you see if they are, failing due to the buckling prior to reach the yield point sigma yp, obviously it is in the strut part. So this is, you see, the criteria through which we can say that, yeah, this is not a column, this is the strut, because they have, you see, they are failing under the buckling load, irrespective of what are the kind of things are there. So what are the kind of other parameters are. So now you see the buckling occurs owing, to one of the following reason. Because you see, obviously when a strut is failing by buckling, so we have to be, as I told you, it's a very sensitive thing. So we have to be very careful that what are the basic reasons behind it. So one of the thing is that the strut may not be perfect straight initially. So you see, if the straight is not perfectly straight, means if you see, the stepped part is there, or if any irregularity is there in the shape of the strut, obviously, this could be, figure out in the straight concentration part, or we can say that there may be a chance of failure due to the buckling part. Second, the load may not be applied exactly along the axis of strut. As I told you, see, in the transverse direction, if the load is not exactly applied through the axis, like the compression we are talking like that, if they are not exactly on that particular axial part, because you see, as I told you, that these stresses like the compressive or the tensile, they are the normal stress components, and they have to be, along a particular line. So because these are the axial stresses, so if they are not exactly along the axis of strut, obviously you see, it will just ending towards the eccentricity, and due to the eccentricity, you see, we have a different kind of loadings which we have discussed already in the earlier chapters. So this is the second reason. So the first reason is that if they are not perfectly like the straight one, or we can say the rigid one, and the second thing is that if they are not, the load application is not along one axis. And the third one is that if one part of the material may yield in, the compression more readily than the other, you see, owing to some lack of uniformity in the material property throughout the strut. So this is known as the material nonlinearity. Means, you see, if the material is not isotropic, if material is not behaving perfectly and uniformly all along, you see, the length of the strut, then obviously you see when we are applying the load, at some part we have more distortion, we have more deformation as compared to the other part, and obviously see due to that we have a great chance of failure because of this material nonlinearity, because there is no uniformly transformation of the material is there, or we can say that whatever the microstructures are there of this particular beam, or sorry, this strut, it is not behaving in a perfect this isotropic part, or we have, you see, the different due to the different boundary conditions of the material nonlinearity, we have a great chance of failing part. So these are the three reasons in which we found that the more of it is on the geometry, so we can say it is a geometric nonlinearity, or more of this it is on the material, so it is a material nonlinearity. So material nonlinearity, and third part it is, you see, when the force, you see, or the load action is not along the same line. So these are, if you're talking about a general sense, then you will find that these are three of the key, the parameters through which we can say that there is a great chance of having the buckling in the strut part. In all of the problems considered so far, we have assumed that the deformation on both progressive, you see, with increasing of load, That means you see when you know like increase the load, we are assuming that this stress or the strains which are coming due to the application of load, they are in the uniformly distributed. That means you see they are progressive, they are increasing you see linearly with the linear increase of the load. You know like, and simple in form, that means you see if we assume that a member in simple tension or compression, that means the uniaxial part, it becomes progressively longer or shorter but remains straight. So there are two things you see here. We are not considering any kind of nonlinearity, but you see when we found that if a column you see or a strut is having buckling, there are geometric nonlinearity, there are material nonlinearity, and there are you see the forces which are not exactly on the same axis, and due to that we have an eccentricity, or due to eccentricity we have a buckling in that particular structure. So all these three terms are perfectly realistic way. So, but you see always we assume to make the simplified you know like applications, that okay, now you see these are the simplified assumptions and through which we are generally you know like deriving the equations. So in this particular you know like the segment says that if we assume that a member is in a simple tension or in a simple compression, the progression means you see the stress, you see in even you know like the elongation or the compression, whatever the progression is there in the dimension part, or we can say in terms of the strains, you know like they have to be you know like go linearly, and in the under the load application the you know like this object has to be remain in the straight part. So which is you see you know like it is somewhat we can say the unrealistic in some of the higher load zones. Under some circumstances, however, our assumption of progressive and a simple deformation, again the progression and the simple deformation may no longer hold good and the member becomes unstable. So this is a perfect theory of instability, because you see you know like as I told you, in a realistic way always nature produces maximum nonlinearity in terms of many, you see like you know like a perfect simple example is that the water is flowing from higher to lower. Is it lower to higher? No, nothing is there, because and if we want to do this kind of thing, we need to go against the nature law. That means you see we need to apply an external agency to do this nature. So here also you see if you replicate that particular concept here also, we'll always find that if we apply, like you see we are holding a beam and we are you know like extending that part, or compression is there, always you see some sort of layers are being distributed from their own position, and due to that the object is always tending to move in terms of sometimes microns also, they are not be there in the straight part, you see as the straight beam is there before application of load. So you see here whatever the theories which we applied in terms of the deformation or the deflection, it will not you see you know like remain in the same way. Some sort of you know like the distortion is there due to this particular unstable part, and that's why you know like we need to go with the stability part, and that's why you see sometimes the buckling is there, and buckling is an important phenomena to check it out when a longer membrane is there under the application of load. The term strut and the column are widely used, because generally you see we are termed as you know like this is the strut or the column particular, often interchangeably in the context of buckling of slender members. So you see here, as I told you in the very first slide, that only a buckling is the key phenomena through which we can simply bifurcate that you know like this slender member is coming under you know like the column, and this slender member is coming under the part of this strut. So at values of load below the buckling load, a strut will be stable equilibrium, where the displacement you see caused by any lateral disturbance will totally recovered when the disturbance is removed. So that's what you see here. We apply the load, and generally that's what you know like we can say that from this statement that we apply the load and the elastic deformation is there, and you see whatever even the deflections are there, if we release the load, body comes to its original phase without any permanent set of deformation. Whatever the theories which we develop, that means the Hooke's law, and whatever you see the elastic coefficients are there, like the Young's modulus of elasticity or the shear modulus of rigidity, or whatever you see the bulk modulus, all you know like these theories are well applicable, because in that we can say that they hold the good relations between the stress and the strain, and also you see there is no permanent deviations are there in the beam or the column or any kind of membrane. So we can say that for that there is no buckling is there within that elastic deformation, or we can say this is the statically equilibrium position prior to apply the load, you see you know like, and after the application of load up to the elastic limit. So that's what you see you know like we are defining now the reasons when like if the load application is there below the buckling part, the strut will be in an equilibrium position, and then you see whatever the displacements are there, or like whatever the deviations are there, like due to this particular load application, we can say that it can be regained once we release the load. And that's what you see the theory, whatever the theories are coming within that particular region, they are holding good like assumptions, and we can say that this is absolutely okay up to that region. At the buckling, now you see here at the buckling, the strut is said to be in like a state of natural equilibrium, because now we are in the buckling, and buckling is always coming, as I told you, due to the nonlinearity part. And I told you that nonlinearity is always there, or I can say that nonlinearity is well tuned with the natural phenomena. So we can say that at the buckling load, means when you see the strut is there under the action of buckling, the strut is always to be in the state of natural equilibrium, because it is now well tuned to the nature, and theoretically it should be then be positive to gently deflect the strut into a simple sine wave, provided that the amplitude of wave is kept small. So now you see here, once we know that now the buckling is there, and due to buckling now the whatever the like the layers are there of this particular strut is now under the deflection or the deformation, and they are forming, you see, as per the kind of load. So generally we are saying that now this this strut is whole divided into the sinusoidal form, because this is the well periodic phenomena is there. And but you see, we always keep in mind that you see whatever the displacements are there of these particular layers from their own positions, they have to be very like a small amplitude. Then only you see, if it is more than, obviously you see like we are in the danger zone and there is a good chance of failure. So we are just trying to keep this amplitude as small as we can, so that you see whatever the phenomena are coming at the buckling load, it can be easily evaluated. Theoretically, it is possible for strut to achieve a condition of unstable equilibrium with load exceeding the buckling load. That means you see, like if in the theoretical way, again you see the theoretical is somewhat always associated with some certain assumptions. Realistic way is somewhat different than those things, because you see in realistic way we have some sort of real nature nonlinearity is there in those processes. So if we are talking about a theoretical, then you see it is always possible for a strut to achieve a kind of condition in which the unstable equilibrium is there under like when we exceed the load of a buckling part. Because you see, once we go beyond that, then you see we never know that what is the prediction is there of these, you see how like these layers are being like behaved under this particular exceed load like of the buckling. So somewhat we can say this is an unstable equilibrium phenomena if you like apply the load beyond certain like beyond the buckling load. Any slight you see like this lateral disturbance then causing failure by buckling, because you see we cannot predict the behavior of the layers under these heavy load which is beyond you see the buckling. So there is a great chance that actually if we do, and that's what you see like we are sometimes saying that if it is a deterministic phenomena, then what exactly the initial parameter is, and due to that it is very sensitive to that part. So because you see we are already in the danger zone, and now what we are doing, so whatever the action is there against or in favor of that thing lead to a failure. So any slight lateral disturbance, even you see like, so how sensitive it is, you see, simply causing a failure by buckling, and this condition is never achieved in the practice under the static load condition. Because you see under static load condition we know that how when you apply the load in a statical manner, you see because all these assumptions are being carried out with this under a static load. So under the static load you see like we know that whatever like the phenomena are coming, they are not in the transient nature, they are not in the dynamic nature. So we can like keep all these things and we can look at all those phenomena, as I told you that like straight away we can simply figure out under the static load that okay, now this is the elastic region, this is the plastic region, this is the ultimate tensile strength or compressive strength, whatever you see, and then there is a fracture is there in those phenomena. But when we are talking about a buckling part, and if you go beyond that, then you see again under the dynamic load condition where you see like all these deviations are there in the sinusoidal form, and beyond that there is a great chance of failure. And you see in a realistic manner, you see always in the dynamic nature it may happen, but if it is a static load condition, then you see we can simply like control this particular part. Buckling occurs immediately at the point where you see buckling load is read. So that's what you see always, buckling is very closely associated with the buckling load, and buckling load is always gives you that now you see this is a hidden danger part is there. If you reached up the buckling load you see of a particular strut or column, you are always in the danger zone, and if you go beyond that, then there is a certain chances of the failure under the dynamic load condition also. So you see here, buckling always occurs immediately at the point of buckling, and owing to reasons started earlier, that actually whatever the reasons are there due to geometric nonlinearity, material nonlinearity, or you see when the forces are not exactly on the same axis, and due to that the eccentricity is there. So all these are the key reasons through which we can say that the buckling certainly will happen to the strut part. So you see, the resistance of any member to bending is determined by its flexural rigidity. The flexural rigidity is always having two main key parameters. One is, you see, the E, the Young's modulus of elasticity. The Young's modulus of elasticity will give you a clear reason about the elastic deformation. Once you define the, let us say, some value is there. So once you define the value of E, this will give you that now this material is having this much, the relation of the stress and strain in the linear region. If you apply, you see, the load, and you see under the load application we have the stress and strain, and this, you see, the relation of the stress and strain is going beyond certain part, and certain part means now going beyond the value of E. That means, you see, you are now going into the permanent set of deformation. I is nothing but, this is the area of cross, this is the area moment of inertia. So again, you see, in that we have to be very, very careful that actually what exactly, the shape of this object is, because based on the shape we know that how the fibers or the layers of these fibers are being set up. So if you apply the load, let us say the compressive or the tensile or the shearing part, then we know that how these fibers will react because of the shape of that. So shape is also an important aspect, and which we are computing, you see, in terms of the I, which is nothing but the area of moment of inertia. So this, you see, the whole term E into I is known as the flexural rigidity, and this is a limiting reason, I should say, you see, under the load applications, through which we can say that, yeah, this is, you see, the resistance is can be provided by the material. So again, you see, this EI is very sensitive to the which material which you are using and what is the shape. So E is the Young's modulus of elasticity, as I told you, and I is the quantity which can be write as a AK square. So I, which is the area, area of the moment of inertia, is equal to the area of cross section, that whether you are using the circular cross section or whether you are using the rectangular cross section or the triangular cross section, whatever you see the kind of column or the strut is there, accordingly we can simply use this area, and K is the radius of gyration. That means, you see, where you see the the mass moment of the center is there, and through which how you see the moment will be acted in this particular way, so that we could easily figure out that, okay, yeah, these are some of the sensitive reasons where you see the stability or instability can be happen based on the value of K. So this is, you see, the EI, which will provide you the basic domain for having the material property, or we can say that how it can be withstand or the kind of load up to a elastic or the plastic regions. And then you see the load per unit area, which a member can be withstand. You see, the load per unit area for which a member can be withstand is therefore related to K, which is the radius of gyration. And there will be, you see, two principal moment of inertia is there, which we discussed. If the at least of these is taken, then the ratio is called the slenderness ratio. So you see here, one is the mass moment of inertia, one is the area moment of inertia. So we have to be very, very careful that actually what kind of load application is there, and whether we are going in the mass, means the mass is the influencing property, and due to that the inertia forces are dominating in the nature, and then you see if we want to calculate the stresses due to that, then we have to be very, very careful about the mass distribution and the mass moment of inertia. But like the previously, you see, if you are talking about, you see that what kind of shape is there, so you see the flexural rigidity through which we are defining those, you see, because it has a isotropic material property, and you see the area is a dominant parameter in those kind of things, then we have to be very, very careful to check it out the area moment of inertia in those cases. So you see here, and if we are taking at least in one of them, then the ratio is called the slenderness ratio of these, and you see it's a numerical value which indicates whether the member falls into the class of column or the strut. So you see, this is another criteria to check it out whether you see the member is going, because you see, as I told you, the dimensional parameter is very, very important. So you see, we are computing the dimensional parameter through the slenderness ratio. So 1 by K, that is, you see, the length of member divided by the least radius of the gyration. That means what is the minimum radius is there of the gyration through which you see if you are dividing those things, it is known as the slenderness ratio. So based on the value of slenderness ratio, we could easily figure out that whether the member is falling in the column or whether the member is falling in the strut part. So you see here, this was the prime theories, you see that what exactly the meaning of, you see, the column and the strut is. And again, you see, when we describe about the column and strut, we could we found out that actually, you know, like the buckling is the key phenomena. So that's what you see, what are the basic reasons of the buckling, which we discussed. And then you see, we found that again, you see, not only the buckling is the criteria to differentiate out the column and the strut, but also you see the slenderness ratio, which is based on this radius of gyration, is also one of the key factors through which we can say that this member is now falling in the column or this member is falling in the strut. Now you see here, we are going in the Euler theory. So you see here, the strut which fail by buckling can be analyzed by Euler theory. So Euler is given you like the theory through which we can say that, yeah, what is the basic reason, how we can analyze that reason using the Euler theory. In the following section, now the different cases of the structure, you know, like the strut have been analyzed. So what we are doing here now, as I told you, that, you know, like what the boundary conditions are there, and through which now how these, you know, like the buckling will be happen, and how we can stop. You see, once we know that now this is the you know, like we have the member and this is under these conditions, so we could easily limiting the conditions through which we can say that now this is, you see, before the buckling load, and this is the buckling statement is there. So in that category, you see, in the Euler theory, now we have taken the first case as the strut with the pinned end. That means, you see, it is a kind of, you know, like the beam with, you know, like the simply supported part. So here what we have the strut with the pin ends at the extreme ends of the strut. So consider an axially loaded strut. Now you see, simple, the loading is simply axial towards, you know, like the longitudinal part shown below, you see, shown in the next figure, is subjected to an axial load P, and this load P produces a deflection. Obviously when you apply the load along the particular axis, we have, you see, a kind of deflection which can be measured in terms of y as a distance and x from the end. So you see here we are taking, you know, like since you see the this strut is always lying in the x-axis, so always whatever the deformations or whatever, you see, the flow of this strut is there, it is always along the x-axis and the deflection is there, which can be measured in terms of y-axis, because you see both ends are pinned. So when you apply the load in terms of you know, like the compressive or extension, you see whatever the deflection are coming, they are always coming in the perpendicular direction. So you see the deflection can be measured in the y-axis. Assume that the ends are either pin joint or, you see, rounded, so that it is, you see, either you can represent it by any of the way. You can simply say that these are the pin joint. It says that actually it has only 1 degree of freedom which can be go in the x direction, or we can say you can simply, you know, like shown by, you know, like the dot part or rounded part, so that you see there is no moment at either end. So that's generally, you see, we are using that when a simply supported beam is there, the supports are there from the bottom part. But here you see we are saying that, you know, like these are the pin joints. So this strut is just, you know, like hanged under the pin joint action, and the load application is there towards the axial direction. So you see here in front of you, you have this particular diagram which I described in the previous one. You see here, this is the strut, and these two extreme joints are there, the pin joints are there, which is, you know, like showing, and the rounded one A and B, and you see, you know, like these axial forces are being acted, and due to that, since it is in the compression nature, you see here we have a kind of deflection in this way, you see the curvature shape, and we are measuring at the x distance, we have, you know, like the deflection is y, and the total length of the strut is L. The strut is assumed to be initially straight. That is a very common phenomena you generally see in the beam or in any of the slender member. We are assuming that initially there is no deformation, there is nothing is there within the structure of the beam, so it is well stabilized, aesthetically equilibrium part, so it has an initial straight part, and the end loads being applied actually through the centroid of the beam, the strut. So you see here, if you look at this point, then what we have the same, you see, like at the point C, where we can say the maximum deflection is there of the y, and again you see, if you are talking about the bending moment, then according to the sign convention, if it is, you see, the concave nature, and if it is a convex nature, then you see the corresponding plus and minus signs are there for these convex and concave shapes of the beam. So same you see here, like the sign conventions which we are using for the strut also. If it is going in this direction, you see, then we have the positive. If it is going in the convex direction, then we have the negative part. So you see either one of them, you see, if it is going, then we are always going for plus and minus. But in this case, you see, like we have, like this shape. So obviously the next one, which is the minus bending moment, is there. So we have to adopt that particular sign convention. So you see the bending moment at point C, like in the previous figure, as I shown you, at the x distance where the point C is there, the deflection which we assumed that the y. So bending moment is obviously the load application P into y, and you see here, like by applied the simple bending theory, we know that we have the simple bending equation using direct integration method, which we discussed, is nothing but equals to m equals to ei into d2y by dx square. So again the same theory which we applied here, ei d2y by dx square is equals to m, and m you see, like if we are calculated at point C, this is minus py. So again if you are replacing this m here, we have ei into d2y by dx square is equals to minus p into y, and as I told you that minus sign will be there according to the sign convention. So this equation, you see, m is not a function of x, because you see when you apply the load, there is a great chance of deviation in the deflection in terms of only y. So you see here, whatever the change will come, it is a function of y only. Therefore this equation cannot be integrated directly, because you see here, whatever the this domain which we have taken, d2y by dx square, it is the domain of the x. But since you see here this m is not the function of x, so we cannot directly integrate those things. So you see here, the direct integration method is not like applicable in this case, and then you see the deflection of beam can be like using the different part. So here, as far as this equation is concerned, ei into d2y by dx square, which is there in the x domain, plus py equals to 0, because you see there is no direct integration is there in that way. So though this equation is in y, but we can say, you see, at this stage where the deflection would be maximum or minimum, because you see here we never know that actually how these like the forces will act on that particular part, and what is the basic area through which we can say that, yeah, this is the potential area where the maximum or minimum deflection is. So the above differential equation can be like arranged in the following terms. So you see here, now we are rearranging the equation so that you see we could easily figure out that what are the potential areas where the maximum or minimum the deflection is there. So for that, you see now what we are simply using an operator. Operator is, you see, d by dx is an operator. So if you put at that particular part, then you will find that this d square plus n square into y will be equal to 0, where n square is the new term which is equals to p by ei. P is the applied load is there, and ei is the flexural rigidity. So with the using of this operator and with the using of this the term n square, now you see we have the new term, and this is the second order differential equation, d square plus n square into y, which is equals to 0. Which, as you see, like because this d square is there, so obviously it is d2 by dx square. So we have a second order differential equation which has the solution of form of consisting complementary functions and a particular integral. Because you see, like whenever we are talking about a linear second order differential equation, we have a CF and a PI, which is a very common like phenomena to calculate those things. But for time being, you see what we are doing here, we are interested in the complementary function, because like in that case we have PI equals to 0 in like the differential equation is equating to 0. So you see here, come to the main equation, what we have d2y by dx square, which was, you see, the d square plus p into y by ey, because you see the n square was there. So d2y by dx square plus py divided by ei is equals to 0. So now this is, you see, the second order differential equation. So now you see our main intention is to find out the complementary function. So you see here, simply you need to like replace this y equals to whatever the displacement, the deflection is there in the y direction, y equals to a cos nx plus b sin nx, where a and b are, because you see it is in a sinusoidal form, it is in a periodic form, so we can simply replace. This is a very common, you see, the standard solution is there for any kind of second order differential equation. So this y, which is the deflection, input deflection, is there. We have, you see, a cos nx plus b sin nx. So you see here, now with the application of all those load conditions, what we have y equals to a cos square root of p by ei into x. So you see, like n square, as we discussed, it was nothing but equals to p square by ei. So if we can simply replace this n by square root of pei, so we have y equals to a cos square root of p divided by ei into x plus b sine of square root of p over ei into x. In order to evaluate the coefficients a and b, because they are you see coming according to the equation, so we need to find out what exactly the meaning of this a and b. So we need to apply the boundary conditions of the strut. So you see here, if you look at the strut, we have the pin joints. So at the pin joint, you see, like in simply supported beam, we know that there is no deflection when the pin joints are there. So you see, at x equals to 0, we know that there is no deflection, so y equals to 0, and at x equals to L, that means at the extreme other corner, you see, there is no deflection, so y equals to 0 also in that case. Applying the first boundary condition where x equals to 0 and y equals to 0, we simply get the a equals to 0. You see here where like the x equals to 0, so cos 1, so cos 0 is 1, but sin 0 is 0, so obviously a equals to 0. Now you see here we have b sin when x equals to L with another condition where you see x equals to L and y equals to 0. So you see here what we have, since a has already gone, so this a cos and L will gone out, so we have b sin square root of p by ei into L is equals to 0. And you see we can say that either the b is equals to 0 or the another function which is sin into L into square root of pi is equals to 0. So either of that, you see, if you are applying, if this b equals to 0, then obviously the y0, which is the initial, means you see the initial condition values will come, and you see the strut will not be buckled yet, because you see it is the initial condition. Therefore the solution required in that particular way, the sine of you see L into square root of p over ei is equals to 0. Because we always want, initially we have already assumed that there is no the change in the dimension is there, or the straight part is there, so there is no importance, or there is no worth to keep the b equals to 0. So obviously the next term will be equal to 0, so we have sine of the whole term is 0, so we have L into square root of p into ei is equals to pi, or we can say n into L. So the pi. So you see here, if we are keeping those things, what we have square root of p into p over ei is equals to pi by L, or we can say that the load where the buckling point is there, it is equals to pi square ei over L square. So this is the load condition you see now, through which we can say that again it depends on the pi is the constant term, ei is the flexural rigidity. That's what you see in the previous slides. I told you that ei is a very important phenomena, and another important phenomena is the length. What is the length is there of the strut part. So we can see that this ei, which is an important parameter as we discussed in the previous slide. So again you see here in the load particular, to check it out the buckling load, the ei will be, again the flexural rigidity will be considered, and the L is an important phenomena, because you see this is the dimensional parameter through which we can say that whether it is categorizing in the the strut or the column. So the L square is there in the denominator. So from the above relations you see which we have discussed, the least value of p which will be caused the strut to buckle is called the Euler crippling load. That means you see this is the limiting part through which we can say that if you go beyond this, then the buckling is certainly there. If you keep you see the load application within that particular part, we have you see there is no buckling is there in that. So that's why you see, since this is a limiting case for the strut, so it is known as the Euler crippling load is there, and from which you see we can say that the PE, which is you see the Euler crippling load, is equals to pi square ei divided by L square. And it may be noted that you see the value of I, which is you see in this expression, is the least moment of inertia, should be taken perfectly, so that what exactly the structure of this particular beam is there corresponding you see because this is the area moment of inertia is there, so we have to be very careful that what exactly the shape of that particular column is. And it should be noted that other solution exist in the equation is also, you see, if it is equals to 0, sin NL is equals to 0. That means you see when we are keeping this square root of p by ei with n, so you see here we have sin a of NL equals to 0. So we can interpret these above analysis in that sense that when the load within the value of the load, if other than those you see the values which make sin of NL is equals to 0, the strut will remain perfectly straight. Since you see we know that this is one of the condition where we have sin of NL is equals to 0, or we can say that PE equals to pi square ei by L square. Here you see there is a chance of the deviation, if you go beyond that, there is a chance of the deviation of the shape of the strut. But other than this situation, we have, you see, in almost all kinds of load where the sign of NL is not equals to 0, we can say that the strut will perfectly remain in the straight position, and we can say that sign y of which is b of, you know, like sign of NL which is equals to 0, we can say that now in this condition, you see, we just try to avoid. So for a particular, you know, like value, in that we have P is equals to pi square EI by L square, or we can say that in another form sin of NL is equals to 0 or NL equals to pi. So we have N, which is, you see, you know, like the square root of P or EI is equals to pi by L. So we can say that the another solution for, you know, like this for a particular value y is equals to b of sin of nx, or we can say that b into sin of nx by L. So you see here what we have another solution by, you know, like keeping that what exactly the meaning of, you see, you know, like the load calculation, and to check it out the limiting part of buckling in that. Then we can say that the strut is in the state of natural equilibrium, and the theoretically any deflection which you know, like it suffers will be easily maintained without any change of its straightness. We can say that these are the you know, like the limiting conditions are there to keep this phenomena in the naturally equilibrium. The solution chosen for this, you see, which we have sin of, you know, like NL is equals to 0. So we can say that this NL is equals to pi is just one the particular solution. The other solution which maybe you see at where you see the sin of NL is equals to 0 is NL equals to 2 pi, 3 pi, 5 pi, each are, you know, equally valid mathematically, and they do affect, you see, you know, like in fact produce the same values of Pi which are equally valid for modes of the buckling of the strut at different you know, like from the simple bow. That means, you see here, as we go in a further analysis, then we will find that, you see, there are another modes where there are, you see, the different kind of, just like it is a simple phenomena of vibration, where we know that at a first natural frequency there is a one mode, at another natural frequency second or third or fourth, you see, we have a different vibrational modes are there. So similarly, you see here, when we know that at NL equals to pi, where you see the buckling is there, a simple mode is there, but as you are going in the 2 pi, 3 pi, 5 pi, then we have a different, you know, like the modal parts are there. That means, you see, we have different modes of these the strut is there. Theoretically, therefore, you see, there are an infinite number of values of PE, each corresponding with the different mode of buckling. So that's what you see here. If we have an infinite means n number of, you know, like the value of PE is there, there are n number of modes of bucklings are there within that structure, and that's why you see, you know, like we can say that in once we calculate the PE, that means if we are calculating EI and L square, these are the significant terms for calculating the buckling in terms of the first mode, second mode, third mode, and then if you are going in a higher range of mode, certainly you see, you know, like the failure chances are greater, and you see, we can say that there are certain parameters which are very sensitive to go in a higher range of modes of the bucklings. The value selected above is so called fundamental you know, like the mode value, and it is lowest critical load producing the single bow buckling condition. Obviously, you see, when we know that, just like in the vibration, we have the fundamental frequency, or you see, you know, like the first mode is there at the particular thing. So same thing here, when we know that at this particular first mode where NL equals to 0, or we can say NL equals sin of NL equals to 0 or NL equals to pi, this is the first mode, we can say the fundamental modal value, and this is also known as the lowest critical load PE, which is pi square EI divided by L square, is the fundamental crippling load is there, the lowest part, and at this particular we have a single bow buckling, as you can see in this particular part. So you see here at NL equals to pi, what we have a single, you know, like the bow is there, and only one deformation is there, which is P1 is pi square EI divided by L square. Second, you see here now, if we are keeping the solution as I told you that for higher buckling modes, then we have NL equals to 2 pi produces buckling in the 2 halves waves. That means, you see, you have two different vibrational modes are there at these particular points. So similarly, you see what we have, you know, like the P2, which is nothing but the 4 times of P1, that means 4 pi square EI divided by L square, always giving you 2 different waves. So we have 2 halves of that. At one, you see the perfect you know, like the wave is there, wavy form, and another one it is a second form. So you see here both the node and antinodes are being formed, and you see the orthogonality conditions are there in the different modes of the buckling. And similarly, you see, if you are keeping the 3 pi which is equals to NL, so obviously the P3 is nothing but equals to 9 pi square ei divided by L square, because now it is in terms of the square terms. So what we have now, we have, you see, the three different modes are there. So you see the the third harmonic terms are there. Harmonics means, you see, the harmonics means the multiple of these natural frequency, the natural we can say the mode of this buckling. So you see here, if you are talking about the second, then we have the second harmonic. If you are talking about the third one, NL equals to 3 pi, then we have the third harmonics of the natural part of this critical load is there at the buckling condition. So you see here we have three shapes are there in which all the nodes and antinodes are being formed at these conditions, and you see here this this crippling load is there, which has the value of 9 into pi square ei divided by pi square ei divided by L square. So now comparing those terms, we know that this NL, which is equals to pi in the first condition, we have, and we need to replace, so L into p square root of p over I is pi, so we have p1 which is pi square ei by L square. So in the second case, you see, we can simply see that when this NL, which is equals to 2 pi, so if you are keeping this n, which is like square root of p over ei, and by keeping L, we have L into e square of p over ei, which is equals to 2 pi. So we have the p2, which is 4 times of p1, or we can say 4 into pi square ei over L square. And similarly for third mode, where you see the this NL equals to 3 pi, we have P3, which is 9 times of pi square ei over L square, or we can say that 9 times of P1. So as you move further, that means, you see, if you are going for higher modes of the buckling, we have always, you see, the n squared terms. That means, you see, if you are going for the 2 or 3 or 4, you see here always it is going in terms of geometrical progression, 1, 4, 9, 16, like that. So you see here we can say that whatever the shapes are coming, that means whatever the wavy features are being approached to the strut, it is very hazardous, because you see all the layers are in like the crippling part. So we have to be very, very careful to design those buckling just to avoid going in the higher modes of the buckling, like for a failure analysis. Come to the second case, where you see, we have one end is fixed and other end is free. That means, you see, just we have a rigid end is there and one end is absolutely free. So you see here, simply we need to write the equations at point C. Again, the same case which we have taken here, the deflection is there in the y direction with the load application P, you see here at this particular point. So here, like this P, the applied load is there. This is the like the fixed part is there, so origin, so we can say that the rigid part is there. So it is sort of like the column which we have discussed. When you apply the load, it's a vertical deflection is there, so we can say that the maximum deflection, which can be always coming at the free end. So we have, let us say, A, the deflection, and the y deflection is there at the x like x distance. So we have, you see, the x distance from the free end, so this is there. So the maximum bending moment, you see here at or we can say the bending moment at point C with the difference of these two, which is nothing but equals to P, which is the load application, into A into Y. So again, you see, after the application of those basic equation of the bending moment, we have E into d2y by dx square, which is equals to P into A minus Y. So just, you see, again we need to arrange that part. So we have d2y by dx square is equals to P over EI plus this this PA divided by this EI. So if we rearrange this, then we have the final part is d2y by dx square plus P times of y into y over EI is equals to P into A over EI. Now you see here, again we need to compose those things here, that okay, the n square, which is pretty common, P over EI is there, and by keeping the differential this originator, means if we have, you see, D, which is equals to d2 over dx square, the operator, we have, you see, in the operator form D square plus n square whole as into y is equals to n square A, because now you see we have the additional deflection is there at the free end due to the load condition, and it is A. So obviously we have n square into A. So now you see with this equation, now we would like to formulate the solution. So the solution of above equation, which is D square plus n square as a whole into y is equals to n square A, this equation would be consist of the complementary, the solution will be having the CF and the PI value, the complementary function and the particular the solution. So you see here, for the particular value and the complementary functions, again we need to generate that particular generalized solution. So y generalized is equals to A cos nx plus this B sin nx plus pi, the particular integral. So particular integral value of y which satisfies the differential equation is always, you see, like since it is the free end is there, so y of particular integral is equals to a, which has, you see, the free end amplitude is. So therefore you see we can simply write the complete or the generalized solution of the equation above, y equals to a cos nx plus b sin nx plus this a, because it has the pi has a value of a. Now you see we need to impose the conditions of the boundary, because you see we have one end is rigidly fixed up, one end is free absolutely. So obviously see now we have different conditions altogether here. So first if we apply x equals to 0, you see where the rigid end is there, we know that there is no deflection because of the rigid fixed end is there. So you see here when we keep that y equals to 0 at x equals to 0, we have the value of a coefficient a, capital A is equals to minus a. Now you see here at if you are coming to the same condition where x equals to 0, this is the fixed end, so obviously we have the slope 0. So again we can say that at x equals to 0 dy by dx is equals to 0, which will give you the another coefficient value b is equals to 0. So by keeping those conditions we have the generalized complete solution of the equation y equals to minus a cos nx plus a. And you see here another condition which we can apply here at the extreme free end. So you see here where at x equals to L we have the free end, so deflection will be equal to a, which we have already computed that part. So by keeping that value we have a which is equals to minus a cos nx plus a. So if you are keeping at x equals to L, we have this y value is a. So you see here cos of NL is equals to 0. Obviously see cos is always 0 at pi by 2, so NL is equals to pi by 2. N is, we know that this n square is p over ei, so square root of p over ei into L is equals to pi by 2 sorry. Therefore the Euler crippling load for this condition where the one end is fixed, one end is free, the PE is equals to pi square ei over 4 L square. So you see here now by applying the different boundary conditions, now the crippling load is absolutely different, but the main parameters are again the same. Ei and L are the responsible parameter for this kind of conditions. The third part is when the strut with the fixed ends are there. That means you see here we have a strut, instead of you see the one end free, both ends are fixed. So due to the fixed ends, you see, like the supports, bending moment will also appear at the supports, and since this is, you see, the property of the supports are there, so they will apply simply the moment, because this is not the pin joint, they have a rigid ends. So obviously you see the bending moments are there, so we need to consider. So you see here the load application is there at the two extreme end, and because of the load application these have the fixed, like rigidly supports are there. So this will be, like the uniformly distributed, and we have, you see, the deflection like in this particular y direction. And if you are computing at the point C, where from the x distance, like from the one end, so we have, you see, the y deflection is there, but it is also having, the bending this moment is there at this particular extreme end. So we can say that the bending moment, the equilibrium bending moment at point C is nothing but equals to the m at the extreme end minus p into y. So you see here with that consideration, again you see the same equations which we need to apply, E into d2y by dx square, which is equals to m minus py. So this is the equivalent, like the bending moment is there. Again what we have the same equation, d2y by dx square plus p over ei is equals to m over ei. Now we know that the n square is nothing but equals to p over ei, this p over ei. So we need to convert this in the operational form, the operator form. So we have d square plus n square into like the y is equals to m over ei. We have, you see, like the two main things, one is the complementary, one is the particular integral form. So you see here the ypi is nothing but equals to m over n square ei plus m over p. So you see here with that we can simply replace this thing is in terms of the complete solution, or we can say the generalized solution. So by keeping ypi, which is nothing but equals to m over n square ei, or we can say m over p. Here we have y equals to b cos nx plus a sin nx plus, you see here, m over p, or you see with the, applying the boundary conditions, because both ends are rigidly fixed up. So at x equals to 0, you see we have y equals to 0. So we have b which is equals to minus m over p. So by keeping that condition, what we have, we have simply one coefficient which has a value of minus m over p. And by keeping it x equals to 0, there is no slope because of the rigid boundary conditions. We can say that the another coefficient a is equals to 0, and then you see what we have y which is equals to m over p 1 minus cos of minus nx. So you see here it may be clearly noted that at x equals to L, that means again another fixed rigid end, there is no, you see, the deflection as well as the slope. So you see by keeping those conditions, we can simply figure out that we have m over p into 1 minus cos of nl is equals to 0. So either of the term is 0. So we can say either m over p is equals to 0 or 1 minus cos of nl is equals to 0. So obviously you see the moment and the load cannot be 0, because due to that only the deflection is coming. So we can simply ignore this condition. So we have the final condition 1 minus cos of nl is equals to 0, cos of nl is equals to 1. So obviously you see it is equals to 2 pi. So we have square root of p over ei into L is equals to 2 pi. So buckling load, or we can say the this Euler critical load when the both ends are fixed, are Pe equals to 4 times of pi square ei over L square. So it is, you see here, when we have, you see, both ends are fixed, like the pin, you see pin joints are there, then we have pi square ei over L square. When one end is free, then it was, you see, and one end was rigidly fixed up and the P load is there, then the crippling load was there, pi square ei over 4 times of L square. But when both ends are rigidly fixed up, then we have Pe is 4 pi square ei over L square. So now you see here we are going to discuss that when one end is pin joint and one end, like, is free, then what will happen. So all, you see, like the different boundary conditions are to be incorporated, and we just want to like describe the crippling load, so that you see whenever the realistic applications are there, we can avoid these buckling conditions in the way to safely design about the strut part. So in this, you see, the lecture we discussed about the main strut and column, and also you see that what the importance of the buckling load is there, and what are the influencing, or we can say the dominating parameters are there in that, and also you see what are the root cause for buckling. And apart from that, you see, we also discussed about the main boundary conditions in the realistic way, that if we have, you see, like both ends are rigid or both ends are pin joint, and if one end is free and one end is rigid, then you see what is the value of the crippling load is. So in the next lecture, you see, again we would like to check these crippling load for the different boundary conditions, and then you see, we will go for the numerical problems of that. Thank you.
Thank you.